constructing truth tables. This is how we'll show validity in other argument forms other than our categorical syllogisms. What are truth tables? Truth tables are a diagramming technique to show the validity of arguments that are not categorical. These other argument forms are constructed from propositions that contain other logical operators like disjunctions using or statements, or conjunctions using and statements or conditionals and implications. Those are the if-then statements. So the truth table is a chart containing columns marked out with the terms of the argument and the conclusion of the argument that we attempt to verify. The truth table is designed to show all possible cases of truth values with the terms. Once the truth table is established, then the conclusions drawn from it are valid in all possible cases. So in this case, if we're doing a truth table, you prove it once, so you do a truth table up for an argument form, and you show its validity in the particular instances or situations that you show, then that is valid for all time. So it doesn't matter whether using different terms or what have you, as long as it fits the format, then you've proven it and it will stay that way forever. So basically you're discovering the truth of whether an argument form works, and then once you've discovered it, you can always refer to it and say, look, I've proven it before, see, this fits the form, and there we go, there's the truth. So again, if you construct a truth table for a disjunctive syllogism, so let's say, for example, an either-or argument, then what you find as being true in the argument will hold whenever you encounter another disjunctive syllogism. So again, you formulate an argument as an either-or argument. The next time you come across another either-or argument, you can say, yes, this is valid in this case because we've already proven it already. So, to set up the basic truth table, start with a chart. All right, it's a table set up with columns for each of the terms in the argument, and there are two possibilities in any one of the cells, and two terms for a possible combination of 4 rows. So in this case, we'll have two situations, true or false. Right? There's only ever two possibilities. It's either true or it's false. And in this case, we're going to have two terms, all right, in our argument. So that means we need to set up a table with 4 possible rows. So our two terms that we're going to start off with, we're going to have a P. All right, we're just going to use some variable names to represent the terms in our argument. So we'll start off with P. We'll have another term we'll call Q. All right, and there's our two terms. And then we set the first row by setting the two terms to true with a T marker. So I'm just going to start off with the first row in our truth table. And we'll mark off the first term true. All right, so here's a situation where we might have an argument that's a disjunction between having either a P or a Q. We'll set it up with the truth that P being there or being present in this one instance, and we'll also set it up where we have the Q in this instance as well. The next row, what you do is you will vary the terms and set it false. So in row 2, we'll have a true for the P. We'll mark the Q false. Row 3, all right, we'll vary the next term. So where we varied Q by setting it to false, we're going to do the next term. We'll set P to false, and then we'll put Q back to true. All right. So again, we're only varying one term at a time. Row 4, our last row, we're going to set both variables here to false. All right. So really what we've done is we've cycled through all the various possibilities with our two terms. So starting off with both terms true, then one term false, then the other term false, and then seeing what happens if they're both false. This is really the same thing as a binary count. So any of you that are familiar with mathematics, for instance, or computer science, all you're doing is counting in binary. So 0, 1, 0, 0, 0, 1, 1, 0, etc. Right? 0, 0, 0, 1, 1, 0, 1, 1. So you can always go about this in the opposite way also by starting off with two false conditions, working your way to the true conditions as well. It doesn't really matter how you want to do it. But again, it's about making sure that you cover every possible case. And so each one of those rows should be different from the other, and you should have as many rows as you do possibilities, right? So it's always 2 to the power of however many terms you have. So 2 to the 2 gives us 4 rows. If you had 3 terms, then what you would do is take the 2 possibilities, raise it to the power of 3, that would give you 8 rows, and so on and so forth. So another term would bring us up to 16 rows, another term would bring us up to 32, and so on. So here's what it looks like with our binary count, except using false and true. Right? False, 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 true, true, false, true, true. Alright, so let's look at our first other possible argument form. Let's look at disjunctive syllogisms. Disjunctive propositions are statements that contain choices. These are either or statements. So for example, here's an argument. You have cake or ice cream. This proposition is usually represented by the symbolism, P or Q. Where P we're going to use to represent cake, Q is what we're going to use to represent ice cream, and we include the logical connector. It's just a small b in between the two terms, and that's what we call an or statement. Generally, we use the lowercase letters in order starting from the letter P. So if we're dealing with 2 terms, we have P and Q. We've got 3 terms, we go P, Q, R, and P, Q, R, S, and so on and so forth as we add more terms. All right, so always lowercase letters starting from P. Now, here's our example again. All right, you have ice cream or cake. You do not have ice cream, therefore you have cake. Now, the symbolic translation for this argument looks like this. All right, again, P is going to represent ice cream in this case. Q is going to represent cake. And our statements are going to look like this. We have P or Q, and then the next line, right, where it says we do not have ice cream, well, we put the little cedilla mark in front of the P. This represents a not. All right, so we have P or Q in line 1, not P in line 2. Therefore, right, so we use the mathematical therefore sign, Q. All right, so you have ice cream or cake, you do not have ice cream, therefore you have cake. P or Q, not P, therefore Q. All right. So, looking at our translated argument, all right, in its symbolic form, we generate a truth table that looks like this. All right, where the T stands for true again, right, in this truth table, and this means the term exists in the argument in this situation. So the F stands for false, and this means that the term does not exist in the argument. And so in row 1, we start off with the possibility that we have our ice cream, right, where P is present, and Q, our cake, is also present. And so according to our statement here, right, we can verify that the initial proposition that we have, P or Q, is actually true, because we actually have both in this case. Right, so in line 1 here at the very end, it says we have P or Q. Well, you look back in the term columns, you say, yes, we have a P, yes, we have a Q. So yes, everything works out. We do have all of those possibilities. All right, thus the argument, if made according to row 1, would be valid. All right, so let's look at row 2. All right, in row 2, the argument is made where ice cream is present and cake is not present. All right, so here's a situation, where you have a statement we've made P or Q. Yes, we have a P. No, we don't have a Q. Is the statement true that we made? Well, yeah, right? We can verify that the initial proposition we have P or Q is true because we have P. Thus, the argument made according to row 2 would also be valid. All right? Now, row 3. Row 3, the argument is made where P, ice cream, is not present and cake is present. Now, we can verify that the initial proposition that we have, P or Q, is true again because we have Q. Thus, the argument if made according to row 3 would also be valid. Right? So there's also a truthful statement P or Q here. Alright, now let's look at the last case, row 4. Now row 4, of course, I'm sure you know where this is leading to. In row 4, the argument is made where P, the ice cream, is not present, and Q, the cake, is also not present. And so we cannot verify that the initial proposition we have, P or Q, is actually true, because we have neither P or Q in this case. Thus, the argument made according to row 4 would be invalid. Alright, so if you make a statement, P or Q, and then you look in the column in the situation where you say, no, I don't have P, no, I don't have Q, well, obviously the statement that you have P or Q can't possibly work out, right? And so therefore this whole thing comes crashing down. Now, if you look more towards in relation to the disjunctive syllogism that we made, right, where we have P or Q, not P, therefore Q, well, this actually fits the situation for row 3. Alright, so if we look at row 3 here, we made the statement P or Q. It's a truthful rule that we've made. And we look at P. Well, P is false, right, in row 3. And so we look back at our syllogism. We say, yes, we can verify that we don't have P. And so the conclusion that we should be able to make from this syllogism is that we will have Q. Well, all things considered, if P or Q is true, and not P, right, is true, right, in this case, we don't have the P, then we should be able to verify that we actually have Q. And in row 3's case, we do have that possibility, right, and that we do have that case. And so according to row 3 in the disjunctive syllogism truth table, we know that this disjunctive syllogism actually works, all right? Similarly, if we go back to, say, row 2, all right, and let's just say we make the syllogism P or Q, not Q, therefore P. Well, in that case, it also works, right? We have P or Q being a truthful statement. If we actually looked at it and said, hey, we have, not Q, and then we look to see whether we actually come up with a P in the end, well, yeah, of course we do, right, in row 2. And so this is how you use the truth tables to actually prove the truthfulness of any situation that you have. So if you make an argument where you say you have cake or ice cream, you don't have cake, therefore you have ice cream, well, you say, well, is that really truthful? Well, you look back on the truth table and say, yeah, it is truthful. Right? That is the case that we must logically come to. Right? That's the conclusion we naturally must conclude. And so that's how you prove a disjunctive syllogism. The only case where it doesn't work is if you make a statement saying that you have P or Q and that you don't have either of those terms. Right? If you don't have either of those terms, then you're really up the creek and you can't verify any conclusion you could possibly make. And so therefore, again, row 4 is the big no-no when it comes to disjunctions. All right, let's look at our next argument form here. We have implications. This is also known in Latin by the term modus ponens. And here's an example. If you have cake, then you will have ice cream. You have cake, therefore, you have ice cream. This is probably one of the simplest implications you can make. This is the if-then case. If you have what is called the antecedent, right? So the statement at the beginning, right? The precondition, if you will, leading to what we call the consequent, right? Or what happens in the end, right? The outcome of the situation. So if you have the antecedent, then it will lead to the consequent, right? Is the idea. So if you have cake, then you will have ice cream. The symbolic translation for this starts off with defining the terms again. So in this case, we're going to set our possibility of having cake as the term P. Then we're going to set the consequent, having ice cream, as Q. And so our symbolic translation looks like this. P, if P, then Q. P, therefore Q. All right, so the first line there shows us our symbolic translation. We use our P term, and we have our Q term leading towards that Q term. And the little symbol that you see in between is a little sideways U. All right, so that little sideways U, shows the direction in which this goes. It's symbolism, more specifically geared towards logic. So if you look through a logic textbook, that sort of thing, you're going to see this little sideways U marker. And that's what that means, right? It defines what we call an implication. This leads to that. P leads to Q. If P, then Q. Okay? So just like before with the disjunctions, we're going to test all possible conditions where if we have P, it should lead to Q. All right, and we'll test the rest of the implication that you see here, the if P then Q, P therefore Q condition according to that truth table in the end. So let's look at the truth table first of all and see what we've got. In row 1, the argument is made where P, our cake, is actually present. And our Q, the ice cream, is also present. And so we can see then and verify that the initial proposition that we have, if P then Q, works, because we have both in this case. All right, thus the argument is made according to row 1, right? If you have the P and it leads to the Q, then the statement, if P then Q, is actually true. And therefore, in this situation, if you have those things set up in the way that you see them in row 1, the argument would have to be valid. All right, so let's look at our second row. In our second row, the argument is made where P, our cake, is present, and Q, our ice cream, is not present. So the initial proposition that we have, if P then Q, is the stated rule. Now, since we have P according to the stated rule, we should have Q. But in this situation, we don't have Q when we actually should. So thus, the initial proposition can't possibly be true. Right? We stated that if we have P, then it should give us Q. In this case, we had the P, but it didn't lead us to the Q. And so we have to go back to the original proposition and say, no, this doesn't work. If we state that P leads to Q and we have the P and it doesn't give us a Q, then this is wrong. And so the argument if made according to row 2 would be concluded as being invalid. All right, so let's go back through to row 3 now. All right, here's where things get a little funny, but if you think about it, all right, it's not quite so bad as you think. Now the argument here is made where P, the cake, is not actually present, but in this case Q, the ice cream, actually is present. Now you go, that's kind of funny, right? That we could actually say that if P then Q is actually truthful, if we don't start off with cake. Well, again, we have P, if we do have P according to the stated rule, we should have Q. But in this situation, since we don't have P, really the initial proposition can't be applied. Thus, the initial proposition still holds true. All right, so, you could liken it to the idea, if you come up to a stop sign, then you will stop. All right? Well, that's the rule, but, let's just say you're driving along down the road and, you just keep going. Well, the only thing I haven't said is you haven't come to a stop sign. Right? And if you don't come to a stop sign, why would you bother to stop? Right? And so the idea here is the stated rule is true that if you come up to a stop sign, then you will stop. But if you're driving down the road and there's no stop sign, then really the rule doesn't apply. And so the rule is true, but in the situation that you're dealing with, you don't come across the case, so it doesn't really matter, right, whether you stop or not, because you could stop, right? Car comes up in front of you, you need to stop, but there's no stop sign, right? You can still stop, but, the rule doesn't necessarily, it doesn't become broken because you haven't actually used it or applied it. And so that's the The funny thing with implications in the truth table is that if you don't have the antecedent condition, it doesn't really matter in the end whether you have the consequent or not. The consequent can be truthful, the consequent can be false. All right, but if you don't have the antecedent, you can't apply the rule, and so there's no way to test it. And so the assumption is at that point that the rule still is applicable and it's still true, even if you don't have the antecedent condition. So the argument if made according to rule 3 actually is valid. Now looking at row 4, we have the same situation, right? The argument P is not present. Q, on the other hand, is also not present. And so again, the initial proposition that we have that, if P then Q is the stated rule, since we don't have P according to the stated rule, we should have Q. In this situation, we don't have P, neither do we have Q. The initial proposition can't be applied, and so the initial proposition still holds true. Therefore, the argument if made according to row 4 would also be valid. Now here's another truth table that we can make up. In fact, it's another argument form. All right. Actually, let's go back to the previous one. All right. Looking at the implications here, you have we didn't actually verify our actual argument. Right. So our argument, the basic modus ponens argument, is if you have P then Q. You have P, therefore Q. You can see that this particular version of the argument is valid, all right? Because if you go to the truth table, you can verify that this situation happens. That yes, you have P, then Q. It's true that you have P. It's true that you have Q, and according to row 1, this form of the argument will actually work. All right, so that's how you verify according to the truth table that the implication works and that this argument form is actually valid. All right, so let's look at another argument form. This one's called denying the consequent. It's known in Latin as modus tollens. Now here's the example of what denying the consequent looks like. So we start off with the proposition, if you have cake, then you will have ice cream. You do not have ice cream, therefore you do not have cake. Alright, so it looks similar to the implication, to modus tollens, or to modus ponens, but if you notice the second line, the second proposition, actually denies the consequent term. Alright, so instead of, before with modus ponens having the cake leading to the ice cream, we're actually going to work this in reverse, where we deny that we have ice cream and try to make the conclusion that we don't have any cake. The symbolic translation for this argument looks like this. First, to start off, we'll define our terms again. So P is going to be cake, Q is going to be our ice cream. And so the symbolic translation looks like this. If P then Q, so the same as before, we have the same proposition as modus ponens, where we had the implication if P then Q, right? P leads to Q. But now here's where you see the difference, right? The second line, the second proposition, states that we do not have our ice cream. So there is no ice cream. And the conclusion that we make, therefore, there is no cake. Right? So not P. So if P then Q, not Q, therefore not P. So our truth table, and well, it looks a little different because of the way I put it here. It really isn't any different than we had before with our modus ponens argument. In fact, the truth table for our implication is exactly the same. All right, so if you look through rows 1 through 4, right, the truth table is set up in the exact same way with the P and the Q, so true, 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 false, false, true, false, false. And if you look at the conditional at the end, where we have if P then Q, the truth table again looks exactly the same. So if we have P then Q, it's true. In row 2, if we have P but we don't have Q, then it's false. If we have P, or we don't have P and we do have Q as we see in row 3, then the implication of P then Q is true. If we don't have either P or Q, again, looking at our if P then Q statement, it's also true because again, remember the rule can't be applied. Now you're going to notice that, again, we have that exact same truth table as modus ponens, but we've actually added 2 more columns. So I've added 2 columns here. So there's column 3 and 4 that are marked off as not P and not Q. The columns really shouldn't throw you for too much of a loop, because really all the columns are is the exact same, or the exact opposite of what you see in our positive columns. So where we have positive Q, positive P, the third and fourth columns there are actually just the opposite of what you see in those other first 2 columns. So in the case of row 1, where we have P and Q being true in column 1 and 2, well, column 3 and 4, not P and not Q, the truth values have to be exactly the opposite. So the truth values are opposite of what's found in the positive columns. And so if you go through the column, you'll see, on row 2, you have P being true, Q being false, while in the third and fourth row, the not P column is exactly the opposite of the P column, so you have false instead of true, and the not Q column is exactly the opposite of the Q column. So where Q was false, not Q has to be true. So let's look at row 4. Row 4 I've highlighted here, because row 4 of the original truth table for our implication is the situation that demonstrates how this argument form plays out. So our denying the consequent argument, our modus tollens argument, actually looks specifically at row 4, where we had the statement if P then Q being true, right? So we've stated if P then Q, so we know our rule is true here. We look at our other propositions, we have not Q. So we go to our column where we say, okay, under not Q, do we have it? Yes. And we have if P then Q, and then we look at our conclusion, not P. Well, the only row that has not Q and not P, as well as the if P then Q statement all being true, is row 4. And so this shows us that we can make that conclusion. If we state if P then Q, and then we state not Q, situations, all right, where we have those possibilities, where we have, if P then Q and, we only have one situation, where if we have the not P then, or if P then Q and the not Q, and it naturally does lead us to the conclusion of not P, and that's found in row 4. That's the only possibility where it works, and we know it works, right, because the truth table tells us this. And so we know that denying the consequent, this modus tollens argument, is actually a workable, valid argument, because according to the truth table, this argument form is truthful. And so we conclude that this form of the argument is valid. Alright, so let's get a little bit more complex. We have, using our conditionals, right, using our implications here, another argument form that we call hypothetical syllogism. Here's an example of a hypothetical syllogism. If you have cake, then you'll have ice cream. If you have ice cream, then you'll have balloons. Therefore, if you have cake, then you'll have balloons. Alright, so really what we're doing is we're taking a whole bunch of implications, right, implicative statements. We're putting those propositions together to form an argument entirely. And so what we've done is we've connected the first antecedent term, if you have cake, right through to the very last concluding term for having balloons, and making a conclusion that we can link the two together through our middle term of having ice cream. Our symbolic translation looks like this. Define the terms first, so we have cake being P. We'll label ice cream Q, and we'll use the term R for balloons. And remember, we're always using those lowercase letters starting from P. So P, Q, R, we have another term, the S, and so on and so forth, right? But we have our 3 terms, P, Q, and R. Our symbolic translation looks like this. If P, then Q. If Q, then R. Therefore, if P, then R. So our hypothetical syllogisms, our truth table is actually going to look like this. All right? A lot more rows, but it's because we have that third term. Remember, the idea of setting up a truth table is you have to have as many rows as you do to cover the amount of possibilities there are. So in the case of our two truth values, either true or false, there's our two conditions, raised to the power of however many terms we have. So in this case, we have 2 to the power of 3, which gives us 8 rows, or 8 rows and 3 columns, giving us that many possibilities. So again, while it looks daunting at first, it's no different than any other truth table that we deal with. We have those 3 terms. The chart must accommodate those extra possibilities with the extra rows and columns. The table is set up in the same way by varying individual terms to cover all of the possibilities. So in this case, again, 2 to the 3 equals 8, are possible combinations of 8 rows. And again, we vary the terms as we go through. So we start off with false, false, false. Then we vary the term false, false, true. Then we go false, true, false. And down to row 4, we have false, true, true. And you can see the pattern as it develops, right? We're just simply shifting the t, all right, term as we go through each one of the terms, right? The truth possibility. Until finally we work our way from the triple F to the triple T, right? So false, 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 bringing down to row 8 where we have true, true, true. All right, so there's what our, again, our hypothetical syllogism looks like and translating into our truth table. All right, so move it. All right, so let's look at row 1. All right, row 1 shows, all right, that we, start off with false, false, false. All right, so we have our first term p being false, and in row 1, if it's false, then any implication in p as the antecedent really don't apply and are considered to be true. All right, so remember way back, we're talking about our implications. We said that the rule holds true as long as it's able to be applied. All right, so we go back to our stop sign example, or driving down the road. The rule is if there's a stop sign you encounter, you stop. Well, you're driving down the road, you don't encounter a stop sign. Well, does it invalidate the rule that you stop at stop signs? No. Just means that it doesn't apply in this case, and the rule is true, but our situation, it doesn't matter. All right, so in row 1, all right, we have our antecedent condition, P, being false. So really it doesn't matter what happens afterwards, right? If Q is false or true, the statement if P then Q is also true. And consequently, if we look successively to the other one, right, so if Q then R, this is also true because in this case, right, Q is false. Doesn't matter if we have R or not. This is also going to be a truthful statement. And so our final possibility, if P then R, is also truthful because, again, we don't have P, so our rule doesn't apply, but it doesn't mean it's not truthful. So if P then R is also considered to be true. And so really rows 2 through 4, all right, are the same cases above. And so if you work your way through, you're going to see that there are certain false, the first 4 possible rows are all false, and therefore it's going to lead us to a whole bunch of true statements with our Q, and then, varying through our R statement. All right. So, you can again work out the truth values of the first 4 rows as you see here, right? So take a look at it for yourself, kind of work it out for yourself. The only, one to watch out for is row 3, where again you have false, true, false. And, if you look at the antecedent condition in row 3 for if P then Q, yes, it's true, but then the next one, if Q then R, well, we have Q, but we don't end up with R. Right? That tells us that the statement of Q then R is false. But then does P lead to R? According to the last column, well, yes, in this case, because again, P is false, so we don't have that antecedent condition to begin with, so the rule doesn't apply, still valid, all right, so it's still truthful. But what I want you to look at now but what I want you to look at now is row 5. Now, if P, then Q is false, because this rule gets broken, all right, where there is a P but no Q shows up in the situation. All right, so we look here, right, row 5, term 1, we've got the P, but, we don't end up with the Q, and so therefore, our if P, then Q statement, we necessarily conclude to be false, because the truth of having P didn't lead to our conclusion of having Q. It didn't lead to Q, so we have to say that statement is false. Now, if Q then R holds true, because we can show, or we can't show, right, that the rule to be false because we can't apply it without having Q. All right, so if we look, we have Q, we don't have R showing up. Or sorry, we don't have Q, we don't have R showing up. So again, does the rule apply? No, not in this case. Is it wrong to say that if Q then leads to R? No, so we have to conclude it as true. All right, so it doesn't matter in this case because we don't have the antecedent term. It doesn't matter what the consequent ends up being. Now, the last column, if P then R must be false, since the proposition states that having a P necessitates getting an R. Now, since an R is not present in this situation, we must resign it to be a false statement. All right, so we have P, we don't get R in our situation here in row 5, and so therefore the statement if P then R doesn't hold either. Right? We had the antecedent, we didn't get the consequent, so the statement that we've made here, if P then R, actually is false. Row 6. All right, if P then Q is false in this case because we see P, but no Q shows up. All right, and so our statement here, if P then Q, is false. Now, if Q then R holds true, because we cannot show the rule to be false since we cannot apply it without having Q. All right, so in this case, we don't have our Q, but remember, you don't have the antecedent condition. It doesn't matter whether you have the consequent or not. All right, the statement is still true. Now, if P then R is true, because in this case, having P also shows that we have R in this case. So in row 6, P is true, right? R is true. And so our last column here, if P then R, does actually work out as well. So in this case, our row 6 doesn't matter whether we actually have our ice cream or not. We'll still get balloons in the end if we have our cake. As weird as that might sound. Now row 7 looks to be, a workable one here where we see that we have our P, we have our Q, so our first statement, if P then Q, is actually true. Now if Q then R is actually a false statement because we have Q in this case, but we don't get R out of it. And so if Q then R ends up being false. Now, if P then R also ends up being false because in this case we have P, but we don't get R out of our situation here. And so now our last column here ends up being false as well. Now let's look at our last row. Our last row, row 8, if P then R is true because we do see our P, we do get our Q, and therefore we get our if P then Q statement being verified. If Q then R is true, because we see Q and the situation shows R. And if P then R is true, because we see P and the situation also shows R. And so therefore our statement if P then R also follows to be true. So now, of course, what does all this tell us? All right. If we look at our truth table now, I've highlighted in green. There are 4 possible cases in our hypothetical syllogism where we can actually verify truth, right, that the argument actually works. Now, only these rows highlighted in green are situations of a hypothetical syllogism that are actually valid. So, for example, let's use another argument, right, another hypothetical syllogism. If it rains, then apples will grow. If the apples grow, then there will be apple pie. Therefore, if it rains, then there will be apple pie. Now, row 8 shows that it rains, and it leads fully to the conclusion that there will be apple pie. Rows 1, 2, and 4 also show situations where there's no rain, but there are ways that we validly get apple pie. And so the only true instance where we look at our hypothetical syllogism, right? So if we look at the argument way back up at the top there, if P then Q, if Q then R, therefore if P then R follows suit according to row 8. Yes, we do have if P then Q. Yes, we do end up if Q then R, and yes, we do end up with if P then R. So in row 8, we very much get the truth out of that hypothetical syllogism. But again, if we look at rows 1, 2, and 4, all right, 1, 2, and 4 also show us that we can also see that hypothetical being truthful. All right, so if you don't get rain, you don't get the apples growing. If you don't get apple pie, then really any of those rules that we've stated about having rain and apple pie and growing are truthful, right? It's just we don't have them in that situation. Again, it sounds a little funny, but again, what we're trying to do is not verify an actual situation. We're trying to verify whether the rules actually are correct. And in those situations in rows 1, 2, and 4, the rules are actually correct, all right? Even if the situation doesn't allow us to test or verify those rules. However, in row 8, this is where we are absolutely correct. So if we do have all those terms and we verify, of course, all of those statements, we do know that the hypothetical syllogism as an argument in that form actually does work. And so proving other arguments, really this basic tool, the truth table, is useful for proving a whole host of those argument forms beyond what you actually see here. So just as you had, say, for instance, with modus ponens, the truth table with the implication shows us that the argument form modus ponens works, right? So if P then Q, you have P, therefore you get Q, was verified on that truth table for implications. You could also use that same truth table to verify modus tollens, right? Denying the consequent, right? So one specific row out of that truth table actually verified that particular argument form as well. And so there's a whole host of other argument forms beyond what I've given you as an example here, these 3 or 4 basic ones. But you can test pretty much anything, all right, with a truth table. Now, all logical fallacies of formal nature are also easily seen on a truth table. So anything wrong with an argument structure can be shown also with a truth table. So for example, here's a formal fallacy, a formal logical fallacy we call affirming the consequent. If it rains, then the road will be wet. The road is wet. Therefore, it rained. Now, to the unsuspecting, this may sound reasonable. However, on closer inspection, the rule proposed in line 1 states that rain is the independent factor. It says nothing about the dependence of the rain to the road being wet. You could have a wet road without the need for rain, right? So if you actually walk out with a garden hose and spray the road down, yes, the road will be wet. Did it rain? No. And so there's really the sort of natural way of looking at disproving that argument. But if you look at the truth table, all right, so if you look at the truth table for affirming the consequent, right, so let's just say if it rains, we'll state with P, road being wet, we'll identify with Q, and if you look at the truth table, we'll look at our basic implication, all right, so if P then Q. Now our 4 rows, again, map out the truth values, and of course where if P then Q actually works as our conditional. And so if you look at row 1, this is where definitely again it works, right? If P then Q, we have P, therefore we have Q, sure, right? Row 1, all right, shows the correct line of modus ponens. And if you look at line, the other line, line 2, all right, there's where if you deny the consequent, you can actually get the deny the antecedent. Right? So, or sorry, looking at row 4, where you deny the consequent, you can deny the antecedent. Right? So that was modus tollens. But if you look at this argument form, it kind of looks like modus tollens, where we're denying something, right, to get our working with our consequent to try and get to our antecedent. But the thing is we can't just affirm the consequent and get the antecedent. Just as I said before, when we said, that I could spray the road down with a hose, right? It doesn't mean it rains, but the road actually gets wet. And so where we actually see this illustrated as a fallacy, right, why my argument actually is wrong in this form, is if you look at row 3. Right? So if you look at row 3 shows how if we affirm the consequent, right, we don't necessarily get the antecedent. Right? This contradicts the value that we're told in line 3. So line 3 says, therefore it rained, but if you look at row 3 says, yes, if P then Q is true, right? So if it rains, the road will be wet is a true statement. And we go to our consequent, right? The Q statement, the road is wet, being true. But look at what happens with P, right? Trying to conclude that we have P, that it rained. Well, on row 3, it shows us that the situation where P, if P then Q is true and Q is true, P is false. And so there we have an actual contradiction between what's stated in line 3 and what actually happens in row 3. All right, so therefore it rained, but no, in row 3 it says it didn't rain. Well, suddenly we have to resolve that contradiction. And the way we resolve that contradiction is by saying, look, there's something wrong with that argument form. Affirming the consequent doesn't always work. Never works, in fact. All right, so in this case, yes, I can affirm that the road is wet, and I always affirm that it rains? No. And so this shows us also in natural language how the argument actually doesn't work. But also, according to the truth table, we can visually see this and confirm that it doesn't work as well. And so really that's what using those truth tables is all about. This is the foundation of what we call predicate logic. Right? Truth tables is that foundation of the predicate logic, what we call predicate calculus sometimes, where we actually do more rigorous testing of validity for argument forms. Using what we call the rules of replacement later is possible from the validity of argument forms established by these truth tables. But that will be another, more advanced lesson. And so there you have it, constructing truth tables, showing validity in other argument forms.